Hey guys, I'm in chapter 17 looking at number 33 from page 392, and what we're going to be doing in this video is walking through how we are supposed to create a 95% confidence interval. So what it is that we need to check, our conditions and our assumptions, how to construct a model, and then how to explain what that model, what that confidence interval says about our question. Okay, so I'll go ahead and read through this. In January 2007, Consumer Reports published their study of bacterial contamination of chicken sold in the U.S. They purchased 525 broiler chickens from various kinds of food stores in 23 states, and then tested them for types of bacteria that cause foodborne illnesses. Lab results indicated 83% of these chickens were infected with Campylobacter. I don't know how to say that, but some kind of bacteria. So our first thing that we need to do is we need to construct or check our conditions for creating a confidence interval, right? So first step is going to be to check our assumptions and conditions for a confidence interval. So our first assumption that we need to check is the independence assumption. The independence assumption. It's very important that the researchers kept the chicken samples separated, right? So important to keep chicken samples separated. Because if they didn't, right, if there was some sort of contact between their different samples, then there could have been cross-contamination, right? And then in that case, one sample of chicken could have an effect on whether or not another sample of chicken was infected, right? We do not want this to be transmitted from sample to sample. So we hope no transmission from sample to sample. These are the sorts of things that we do have to talk through whenever we work through problems like this. So no transmission from sample to sample. And what we're saying with this is we are assuming independence. Why are we assuming independence? Because it's very important to keep chicken samples separated, because we want to hope that there's no transmission from sample to sample. All right, so there's our independence assumption. Our randomization condition is the next thing that needs to be checked. Randomization condition. The randomization condition is really just our way of saying, well, do we know whether or not our samples were collected randomly? Was a simple random sample used? Well, looking at this problem, it's not clear that an SRS was used. But what we're going to do is we are going to assume the sample from 23 states is at least representative of all chickens sold, right? So we're not this says clear, I think it's supposed to say here. Not clear that an SRS was used. However, we are going to assume that our 23 state sample is representative, right? This is important. It's very important that whatever sample we use is representative of the entire population of chicken. Entire population of chicken, right? Because we want this sample to be representative. We don't want to just come to a conclusion and then at the end of it have to say, well, you know what we found cannot be applied to anything. That's the last thing that we want. All right, next thing that we need to check is our 10% condition, right? And this was a condition that we learned back in chapter 16, the 10% condition. And that 10% condition just is asking us, hey, is the sample that we're using, is that less than 10% of all broiler chickens? Well, yeah. So that's what we're going to say. We're going to say 525, because that's the number of samples we got, is far less is far less than 10% of all broiler chickens. Of all broiler chickens. Okay, and then we've got one more that we have to check, and that is the success failure condition, right? Success/failure condition. And this is the one, again, from chapter 16 that reads, we need to make sure that the number of successes we have is greater than 10, and then we need to make sure that the number of failures we have is also greater than 10. Well, how am I supposed to check this, right? Well, in this case, and we're actually using this is a sample proportion, not a true proportion, so we have to use p hat and q hat. Well, since we know that 83%, is that what they said? Yeah, 83% of these chickens were infected, so that means we've got 525 times 83%. Is that greater than or equal to 10? Well, yeah, it is. And 525 times 0.17, that also needs to be greater than 10. So we get 436, and in this case, a success is it being infected. Obviously, we don't want that in real life, but what we're looking at here is we are testing for infection. So therefore, p hat, which is our success, our proportion of successes, are those proportion of chickens that are in fact infected with some sort of bacteria. And over here we've got 89. 89 is greater than 10. So looking back through this, our independence assumption is a go. We are assuming independence. Our randomization condition, we are assuming that, yes, everything is randomized, so therefore it is representative. The 10% condition, 525, yes, that is less than 10% of our population, so that kind of double checks our independence assumption. And then our success failure condition, yep, our sample is big enough. How do we know it's big enough? Because the number of successes and the number of failures are both greater than 10, right? So all of these successes, all of these assumptions and conditions, they're the first thing that we have to check whenever we are doing when we are working through a confidence interval, right? So part B here, and let's switch to a different color here. Part B of this problem wants us to construct a 95% confidence interval. A 95% confidence interval. And these are just a way for us to say, hey, I am 95% confident that the true proportion of all chickens that have this bacteria lies within this interval, right? An interval, we're going to have a lower bound, and we're going to have an upper bound, okay? So what we do with this for a 95% confidence interval is we take our proportion of successes and we add and subtract 2 times our margin of error, or our standard error, right? So this is going to be 2 times p hat times q hat divided by n. And this is the standard error. That is formula for standard error. So this is going to be equal to 0.83. Again, this p hat represents our sample proportion. This is our sample proportion. And then we are going to add and subtract 2 times 0.83 times 0.17 divided by 525. Multiplying this by its standard deviation. And this is going to give us, when we subtract, we're going to get 0.797. And when we add, we're going to get 0.863. Right? So we think of this as the lower bound, and then this is the upper. Now, the whole point of this whole lower bound and upper bound is so that we can interpret this confidence interval. Okay, this lower bound is, hey, if we saw 79.7% of all those chickens in that sample were infected, or if we saw 86.3%, that wouldn't be weird. That wouldn't be out of the norm, right? So let's interpret what these mean, and that's in part C, how we interpret a confidence interval. So whenever you guys write these out, you're going to use these exact words, and then you'll just replace numbers, and you'll replace the variable that you're talking about. So let's do this. We're going to say we are 95% confident. Why are we 95% confident? Because we're finding a 95% confidence interval. So we are 95% confident that the true proportion, what we're looking for, that the true proportion of all broiler chickens infected with this bacteria, Campylobacter, or whatever, Campylobacter, as they say in Appalachia. The Campylobacter lies between 0.797 and 0.863. We are 95% confident that the true proportion of all broiler chickens infected with Campylobacter, whatever this bacteria is, lies between 0.797 and 0.863. Now, this is not saying that my true proportion is probably directly in the middle. My true proportion is just as likely to be close to 0.797 as it is to be close to 0.863. We are just confident that it is somewhere between these two values. Right? So if you guys have any other questions, don't hesitate to reach out. I'll be certain to do another problem that takes this just a little bit further. You guys let me know if you have questions.